Okay, so in this video, again, continue our journey through Unit 2 Dynamics of AP Physics 1. So in this video, we're going to look at the other type of friction, which is static friction. In the last video, we talked about kinetic, which is what happens when the object is in motion. Now we're going to look at what happens when we want it to begin to move, okay? And so static friction is the force that opposes the sliding of one non-moving surface past another. What it is really, it's the friction that you have to overcome to begin to slide. And so these furniture movers, right? You can see that there's a fourth one on the back side, okay? But the furniture movers help us decrease the amount of friction between the recliner and the carpet, right? If we try to do that, we'd have to exert a lot of force to get it to move because there's probably a high static coefficient of friction or high static friction. By putting these sliders under, the sliders are kind of smooth, and so it makes it easier to slide. Okay, so what happens is static friction will max out before the object begins to slide. So if I'm looking at like a force versus time graph, and what I'm doing is as I'm pushing, right? So force time, as I'm pushing, once it reaches this maximum height, that's when it begins to move, and then it drops down, right? And so this would be our static portion of the graph. And this part right here is actually the kinetic portion of the graph. Okay. Now, in most cases, the static friction is greater than the kinetic friction. So Fs is going to be greater than Fk. Sorry, lost one of my bullet points. Okay. Again, remember, we're looking at the interaction. And that's what I'm saying in most cases, because everybody will be like, oh, but what about here? This static friction was less than the kinetic friction. Well, you got to make sure it's the same interaction, right? So for the same interaction, Fs is going to be greater than Fk. Now, what happens is the equation for the coefficient is, or excuse me, for friction is the same, but the difference is with kinetic friction, all the time we put an equal sign. But for static friction, we'll put this less than or equal to sign, okay? So basically that's telling us that if we're less than the static friction, the object is not going to move. So if our applied force is less than Fs, the object will not, excuse me, can't spell this morning, will not move. Can't write either, right? So it will not move. So if I know that I have to have at least 50 newtons of force to begin the object to slide, and I'm only pushing with 30, there's no motion, okay? It's not moving. And in these questions, our acceleration will be 0, okay? Because we're not accelerating the object yet, right? We're trying to get the push, okay, constantly. So let's look at a static friction problem, okay? And this is an Atwood machine problem, okay? So this says students in physics lab design an experiment to test what is the coefficient of friction with the pumpkin on the tabletop. You can see that they set up the setup in the figure. The basic procedure is to pour sand slowly into the pail until the pumpkin begins to move. The pail with the sand in it is placed on a scale and found to weigh 11 newtons. What is the coefficient of static friction between the jack-o'-lantern and the table? Perfect, because this video is being created around Halloween. We're about 4 or 5 days, 6 days away, 7 days away. Okay, so I'm going to treat this as a single object, right? And so what forces are pulling this object? Going to be the friction, right? And the friction on the table and the hanging bucket. And so I'm going to do my free body diagram. So this is kind of weird. Okay, so I got plus my positive x, but what happens is the coordinate system has to follow through the pulley. And so my positive x actually points down. So the weight of the pail is actually in the x direction as well as the friction. So let me go back and fix my free body diagram to show that these are going to be in the x direction. So my positive is going to be the pail, right? So FG pail. And then I'm going to have my friction, okay, on my surface. Now, what happens is I do need to know what is the normal force here, because when we do the coefficient of friction, okay, we need to know that normal force. So if I do that real quick, it's going to be, in fact, they give you the whole free body diagram for everything, right? And so it's going to be Fn minus Fg equals 0. So Fn equals Fg, which equals mg. So that's normal. That's usually pretty standard. And so now my pumpkin, or my motion, right, of the system is just going to be in the horizontal direction. So I'm going to have Fg pail minus friction is equal to 0. And so Fg pail equals Fs. And so now I can just start substituting in. I got the weight of the pail. Weight is mg. And so this is going to be here. Apologies. This is going to be, yeah. And so it's going to be mu mg.
Teachers, for those of you who are in G Hall, the AC's been reported and help is on its way. Thank you. Have a good.
So we do need to distinguish that the mu mg mass is actually the pumpkin, and then the Fg is the pail. Okay, so we can't cancel those out, but we can't cancel these g's out. And so I get the mass of the pail is going to be mu times the mass of the pumpkin. Okay, and so my coefficient of friction is going to be mass of the pail divided by mass of the pumpkin. And so that's going to be, so I got to find the mass of the pail, right? So the mass of the pail is going to be 11 divided by 9.81. Or here's what I can do. So let's do this. So let's not cancel out the g's, right? Because it's going to help me. I can use the equation, or I can use the numbers that are given to me. All right, so let's change this up a little bit. So if I go way back here, I'm going to say this is going to be the force, the weight of the pail is equal to the mu times the mass of the pumpkin times g. And so my coefficient of friction is going to be sorry, I keep messing this one up. It's going to be the weight of the pail divided by the mass of the pumpkin, essentially the weight of the pumpkin, right? So it's going to be 11 newtons divided by 1.8 times 9.81. And that's going to end up being a coefficient of friction of 0.623. Okay, so so this is a static friction. Again, I apologize for the confusion here, but if I want to use the number that they give me, which for the pail is 11 newtons, I can't cancel out the G value, because then it becomes, right, then I have to go back and add a step of finding what the mass of the pail is by doing 11 divided by 9.81 and then bringing that back in. But if I want to use the numbers given to me, right, I can just simply not cancel the g's out and find the weight of the pumpkin, because that's essentially what we're looking for there. Okay. All right. So again, we're going to keep our journey going. We're going to move on to the videos like connected objects, which is actually what this is. So there's a little preview of upcoming videos. We're going to talk about inclined planes, and then we're going to look at the water line, which is bringing mechanics and dynamics and meshing it into one single